relatively short presentation on Lewis acids and bases, and so far we've covered Bronsted-Lowry definitions, which were all about proton gain and proton loss. Sorry, proton gain and proton accepting. Well, Gilbert Lewis extended that because he recognized that if you were to be considering what we've seen previously, kind of this change, that whilst this was acting as a proton acceptor and therefore our Bronsted base, he chose to focus more on what the lone pairs were doing. And so Lewis acidity is all about lone pairs. So it's a broader definition of acid and base chemistry. So here we are. Bronsted, acids, proton donors, bases, proton acceptors. There's that idea that he's extended it to focus more on the lone pair. And so when we're dealing with acids as being lone pair acceptors, bases as lone pair donors, if you needed to remember that, you've got your two, whoops, obliterated those, you've got the two A's like that, acids, lone pair acceptors, and ultimately you end up with a dative covalent or coordinate bond. So let's see how that ties in with Bronsted and how it extends it. So you can see for the first two, kind of fitting well, talking about that lone pair transfer, talking about the proton transfer. But then when we get down here, because there's no protons involved, we have a problem. However, they are still acid-base reactions because we're talking about the lone pairs rather than the proton transfer. So there's a lone pair on here, it's being accepted in by the B there, and a very common example is this idea of forming complex ions, where my central metal ion, copper, dative covalent bond from the lone pair on the oxygen of water. Extend that slightly, still the same idea. Certainly when you look at organic chemistry, we're often talking about movements of pairs of electrons. Two terms that you'll meet later in the course: nucleophile, phile sort of meaning liking, nucleopositive. So these things are electron rich, they're going to be looking for positive centers, and they're going to donate a pair of electrons to form a new covalent bond. So something like water, the hydroxide ion can do it. There's my ammonia, that's got a lone pair, there's a pair of electrons there, and these could all attack in somewhere else and make a new bond. Conversely, electrophile will be seeking out negative areas, and there's some examples here. So these have to be able to accept a lone pair, so they must have empty orbitals. So if we go back to that copper example, there's an empty orbitals that are available, and the ligands are donating electrons into those. If we think of nucleophilic substitution reactions, which involve carbocations, that would be the SN1 mechanism, which you'll come to learn later in the course. You can see here, there's my nucleophile, this is my electrophile. We're forming a new bond just in there. Right, that's what we've done.